Okay, we'll start the class now. Yesterday's class, we taken up this problem. So I think we already discussed this, and today we'll take up one more problem, and we'll try to see what is the solution for that problem. So coming to this problem, what we discussed in yesterday's class, it is straightforward. He has given the force and deflection, and also of course he has given the ultimate strength and shear modulus and spring index. That is a given data. Using given data, we are able to find out what is the wire diameter, mean coil diameter, number of active coils, total number of coils, free length, as well as pitch of the coil. After that, he asked us draw the sketch of the spring and showing various diameters. So, like what we discussed in the previous class, the wire diameter is calculated based on the allowable shear stress. Once you have wire diameter, then mean coil diameter is calculated based on the spring index. So then number of active coils are calculated based on the deflection. So that's what we did in the previous class. So this is the given data, and this is the formula for the allowable shear stress. So where this K is the wall stress correction factor, it is given by this formula, and we computed the tau, which he has already given. Allowable shear stress is 50% of the ultimate strength, the ultimate yield strength. Then we are taking that 50% is nothing but 0.5. So we got it is 545. From that you substitute in the equation for the allowable shear stress. Then you can solve for the diameter of the wire. Comes out as 6.63 mm. So round it up to 7 mm. Then after that, using the relation between a small d and capital D, we can find out the capital D, that is mean coil diameter. Then number of active coils is based on the delta. Delta is given. So this is a formula for computing delta. So from that, number of active coils is comes out as 8. Then by choosing square and ground ends for the springs, so therefore the total number of coils will become, since for a square and ground ends there are two number of inactive coils, so therefore total number of coils will become 10. Then after that, we computed the free length. Free length is nothing but the summation of solid length plus delta plus axial gap. So that's what we have taken here. We computed all those three parameters, solid length, and this is the axial gap, and delta is already computed, so it comes out as 110. Then pitch of the coil is given by free length by total number of coils minus 1. So that is comes out as 12.15 mm. So once we got all these things, then he asked us draw the spring. So you need to draw the spring something like this, and you need to show the important parameters. That is, this is the mean diameter. You need to show what is the inner diameter, inside diameter of the spring, outside diameter, and then what is the free length and what is the pitch. And of course, this is the wire diameter. You need to show all these parameters for the spring. So you need to draw the spring and you need to show these parameters. If he asks the question, you need to show the dimensions of the spring also. Right? So this is how you can do that. So now we'll move on to the next problem. Same helical spring only, but similar thing only. But only thing is here he has given the data in a different manner. That is the only thing. So you first note it down this problem. So once it is completed, just intimate me. So we'll discuss the solution. So I'll give some 2 to 3 minutes or maximum 5 minutes to note it down. Just note it down this problem and then we'll discuss the solution. Is it over? Surya, అయిపోయిందంట నోట్ చేయడం.
Yes, sir.
Okay, right. So we'll discuss the solution now. It is okay. First, I'll read out the problem, then we'll discuss the solution. It is required to design an helical compression spring for the valve mechanism. The axial force acting on the spring is 300 newtons when the valve is open and 150 newtons when the valve is closed. The length of the spring is 30 mm when the valve is open and 35 mm when the valve is closed. The spring is made of oil hardened and tempered valve spring wire and the ultimate strength is 1370 Newton per mm square. The permissible shear stress for the spring wire should be taken as 30% of the ultimate tensile strength. The modulus of rigidity is 81,370 Newton per mm square. The spring is to be fitted over a wall rod and the minimum inside diameter of the spring should be 20 mm. Design the spring and calculate same thing what we discussed in the previous class, previous problem. Wire diameter, mean coil diameter, number of active coils, total number of coils, free length of the spring and pitch of the spring. Same 6 parameters. Assume that the clearance between extent coils or clash alliance is 15% of the deflection under the maximum load. Here this statement is a different one compared to the previous one. So in the previous problem, we consider that the gap between the extent coil as 1 mm and we can find out the total gap. In this problem, he has given that you need to take clash alliance. That means clash alliance is 15% of the deflection under the maximum load. So that means the total gap is going to be 15% of your deflection under the maximum load. So indirectly he has given like that. Instead of assuming the gap and then calculating the total gap, so directly he has given some constraint or condition. For that we can use that condition to calculate the total gap. Okay, right. So now why I said this is a somewhat different from the previous problem is, in this problem he has given two forces acting on the spring. So one force is 300 newtons when the valve is open. When the valve is in open condition, the force is 300 newtons, and when the valve is closed, the force is 150 newtons. But while discussing about the design procedure for the spring, so the first thing what we need to identify any spring design problem is, we need to identify what is the maximum force on the spring and what is the deflection corresponding to that maximum force. So you need to identify those two things. So now from this you can see that the maximum force is when the valve is in open condition, the force on the spring is maximum and which is 300 newtons. So that means we identify that 300 newtons is the maximum force which is acting on the spring. But what about delta? So he has not given anything delta, but indirectly he has given the delta value. So how I can find out the delta value here? See, you can mention the two lengths of the spring. So now I think I have a picture of that. Okay, so if you look at this, I'll zoom it. See now, so I have something like this. I have a valve. So this is when this is in a valve is open condition. See now you can see that here this is open. There is a gap here. Here it is closed. So that means the gap is closed means the valve is in closed position. So now here I have a spring. So here I have a spring. So now if I apply 300 newtons to the spring, the length of the spring when I apply a load of 300 newtons, it is 30 mm only. The length of the spring is 30 mm. The same thing if I apply 150 newtons, that means in the closed position when the valve is closed, the load on the spring is only 150 newtons. So when the load is 150 newtons, the length of the spring is 35 mm. So that means, see here I can calculate the stiffness of the spring here. So how I can calculate the stiffness of the spring? So while discussing about the properties of the spring, we said that if I plot a curve between load and deflection, load and deflection, we got a line which is called straight line. So this is what we call it a linear spring, and then the slope of this line we'll call it as a stiffness. This is what we already discussed. The slope of line means dp, your k is nothing but dp by d delta. So that is dp means this side. So for the slope is nothing but this is dp, that is change in the load for a given change in the load, and this is going to be the change in the deflection, that is d delta. So now in this problem he has given those two conditions. So now when load is 300, so this is corresponding to the 300, and then the length is something here. When load is 150 here, the length is something here. So therefore the change in length is nothing but your d delta. So what is the change in length? So 35 here and this is 40. So therefore this is going to be the delta value, which is 5. So that means your change in load is 300 minus 150. 300 minus 150, that is dp, change in the load, divided by change in the length, that is nothing but a deflection only. Change in the length is 35 minus 30. So that means 150 divided by 5. 300 minus 150, which is 150, divided by 5, which is nothing but 30 Newton for. Here deflection is taken in mm, so you need to write it as in mm. So force in newtons, so 150 newtons divided by 5 mm, so units will be 30 Newton per mm. So but what is again the formula for k? K is nothing but p by delta. You can use this formula also, p by delta. So then if I take here p max, I need to write it here delta max. So now if I want to find out what is the maximum deflection, then what I have to do, that is nothing but your p max, that is maximum load, divided by your k. K is 30 now. So which is going to be p max is 300 and divided by 30. So therefore the maximum deflection is going to be 10 mm. So delta is given as 10 mm. So like this I can calculate, or else no need to calculate this delta also. If you know the k, you can use the formula as per the k and you can derive the expressions for or you can say whatever you want, number of active coils. In that formula you can use k itself straight away and you can find the number of active coils also. I will show you that how you can do that. So now, okay, we'll come to the solution. So this is one way, it is different. So instead of directly giving load and delta, what he has given is, he has given the load and two different loads and two different lengths. So from this you can calculate the stiffness. So to compute the stiffness, this is the formula. So you need to take change in load divided by change in length. Change in load is 300 minus 150. Change in length is 35 minus 30. So from that you will get the stiffness of the spring as 150. Okay, so now I'll go back to the previous slide again, that the problem description what we have done. Undo this. Okay, yes, this one. Now so here, yeah, that's what we are discussing here. So like I already told, you required p and delta, but here p is given directly but delta is given indirectly, or k is given indirectly, you can say that. So that data is given. Then he has given the ultimate central strength. Of course it is 1370 already given, no need to take it from the data book, you have to use only this value. And he also stated that permissible stress in the spring wire should be taken as 30% of ultimate tensile strength. That means the allowable shear stress is 30% of this 1370. So we can calculate ultimate allowable shear stress. Once you have allowable shear stress, then you can use the torsional stress equation. Then from that you can find out your wire diameter. The first thing is over. Then the second one is here there is another restriction on that. So what is the restriction here? the spring is to be fitted over a wall rod and the minimum inside diameter of the spring should be 20 mm. So here in this particular problem, you put a constraint on the minimum diameter of the spring also. So that means instead of taking any value, so here if the d value is less than 20, which is not inside diameter of the wall spring is less than 20, which is not allowed here. So that means he has put a constraint on the inside diameter of the valve also. So then how we can impose this condition in our design so that you can find out the wire diameter. So that is also we'll see all these things now. Okay, right. So first we'll put the given data in the problem. So load is changing 300 to 150 newtons and the spring length is changing from 30 to 35 mm. Then DI inside diameter he has mentioned it as 20 mm, so we have to take it as 20 mm only. SUT given it as 1370 and G is given as 81,370 Newton per mm square. And also he has mentioned that the allowable shear stress is 0.3 times SUT. So now first step is we need to calculate the wire diameter. So for that first we'll compute what is the allowable shear stress using this relation tau is equal to 0.3 SUT. SUT is given as 1370, also you can get it that value. So therefore your allowable shear stress value is 0.3 times 1370, which comes out as 411 Newton per mm square. Then here it is given DI value. So now I need to use the DI also, so that whatever capital D I got it, so I'll get it from that based on this DI only. So or else whatever capital D, that is the mean coil diameter I calculated, if I use this relation, definitely the DI is more than 20 only. So I have to follow the condition. So I cannot get the value DI less than 20. If DI is less than 20 means our design is wrong. So but why it is wrong? You cannot fit the spring into the wall. So because the wall rod diameter is 20 mm, in order to fit the spring into the wall, so minimum inside diameter should be 20 mm. So right, so that's why we'll use this condition also in this. So that is, we already derived, we know the relation between D and DI. So your mean coil diameter is nothing but DI plus D. So DI given as 20, I'll take it as 20 plus D is equal to D. So I'll take mean coil diameter as 20 plus D. So then this is the formula for our allowable shear stress. Tau is equal to K into 8 PD by pi d cube. So in that, here two unknowns are there for you. So in this equation, you don't know what is K value, you don't know what is small d value. Of course, capital D is also written in terms of small d, 20 plus d only. So it is written as in terms of small d only. So two unknowns, one equation you cannot solve it. So here K is unknown. So you need to compute this K, you require C, that is the spring index. So what is the formula for your K? Formula for K is, so like what is in here in the previous problem. So this is the formula for K, 4C minus 1 divided by 4C minus 4 plus 0.615 by C. So that means to compute this K value, I required C. But in the problem data, he has not given that C value. So or else I cannot compute also with the given data, I cannot compute the C value also. If C is unknown, K is unknown for me. If C is unknown, K is unknown. I cannot determine K value. Similarly, here capital D and small d. So since I written the capital D in terms of small d is also unknown. So that means with one equation I cannot find two unknowns. So then what we'll do is, initially we'll assume this K is equal to 1. So that means what we are doing? Initially we are assuming K is equal to 1 means we are considering only the torsional shear stress. We are considering only the torsional shear stress. We are ignoring the effect of direct shear stress and effect of the curvature. So there is no other way. Why I have to ignore? But actually there are, in case of spring, it is subjected to both direct shear stress as well as shear stress due to curvature. But why I'm ignoring here? If I ignore, is the design is correct? Actually, we don't have other way of designing it. So first what I'll do is we'll ignore that effect and finally we'll determine some diameter and later we'll check whether that the particular diameter is capable of carrying the resultant stress also. So that in that way we can proceed, because here you have two unknowns. Two unknowns cannot be determined using single equation. So we make that assumption k is equal to 1. So now, if I take k is equal to 1, then your tau allowable shear stress computed as 411, then 8 pd by pi d cube. 8 P is P max, which is 300 newtons. Here you can see that 300 newtons. And D we written as 20 plus D divided by pi d cube. So now, if I simplify this, I'll get d cube by 20 plus d is equal to some 1.8587. And if I simplify this further, I'll get that value for d. So now, if I calculate or if I simplify this expression, I'll get a cubic polynomial. If I find the roots for the cubic polynomial, I got d is equal to 3.529 mm. So I rounded it up to 4 mm. So now I got the d value. So now once I have a d value, so then now I can calculate this capital D. I can calculate capital D, which is nothing but 20 plus D. So 20 plus 4, 24. Now if I know capital D and small d, now I am in a position to find out what is spring index. So spring index C is nothing but capital D by small d. So now once I know the spring index, now I'll compute this K. Now I'll compute the K value and then I'll find out what is the actual resultant shear stress. So now if that actual resultant shear stress is less than this allowable shear stress, then I can say whatever diameter D is equal to 4 mm I am choosing, then my design is safe. Otherwise, I need to modify the diameter, means I need to increase the diameter such that the induced resultant shear stress should be less than this 4.411 Newton per mm square. So now that will do in the coming steps. So mean coil diameter, once you know the small d, your mean coil diameter is nothing but 24 mm. So di plus d, which is nothing but 20 plus 4, which is comes out as 24 mm. So now once I know that is d and small d, I will compute the C, which comes out as 6. 24 by 4 is 6. Then K. So for a K, C value is equal to 6. K comes out as 1.2525. Now I compute again this real resultant shear stress just by substituting K is equal to 1.2525. If I do that, if I take K is equal to 1.2525 and 8 PD by pi d cube. So P is 300 and D we computed as 24 and small d we got it as 4. If I substitute that, I got the resultant shear stress is 358.81 Newton per mm square, which is less than your allowable stress. Allowable stress is 411, but with the load of 300 newtons on the spring, even if you consider the effect of direct shear stress as well as curvature effect, the resultant shear stress is going to be only 358.81. So therefore, your design is safe from the strength point of view. So therefore, you can choose this D, small d as 4 mm, capital D as 24 mm. Of course, if capital D is 24, your DI is going to be exactly 20 mm. Your DI is going to be exactly 20 mm. So it is satisfying this criteria also. So that means from the strength point of view, now that design is safe. So next we'll go to the stiffness point of view and we'll try to compute what are the number of active coils. So that's what I written here. Therefore, tau is less than 411 Newton per mm square. The design is safe. Then we need to calculate what are the number of active coils. So this is the formula for the number of active coils. So like I already said, so here delta formula is 8 pd cube n by gd power 4. So this is what we are going to use here. So but here what I do is that 8 into, instead of p here, I can replace this one by dp, that is change in load into d cube n divided by gd power 4. The same formula, the only thing is in place of p I'll substitute dp. Now here instead of delta it is delta L or change in the delta. So you can take like this, change in delta, d delta you can take, or dl instead of d delta. Since he has given the length, we call it as dl. So your dl, so I'll use that formula in that manner, or else I can take, so we derived an expression for k. We derived an expression for k, so you can use that expression also. So I think if I go back one step, so I'll show you how we derive that equation for k, or what is the equation for k. That is the last step in your design of helical spring. Yes. You can use that relation also. So yes, this is all these things are over. Yes, so this is the formula for your k. K is equal to this one. So or else if you want, you can write this one here in terms of c also. So or else if you know k is nothing but gd power 4 by 8 d cube n. So in this formula, you know k, you know g, small d is known to you, capital D is known to you, only unknown is n. You can use that formula also. Either way, you are going to get the same answer for active number of coils. So, okay, if I come back to that one, yes, here. So I use the first one, or else if you want to use in terms of k also, no issue. 300 minus 150. Here I have to take 35 minus 30. So this is the change in length, and this is the change in load. So in this equation now, the only unknown is n. So now I can compute the n value, which is nothing but the number of active coils in the spring. So if you calculate this one, it comes out as 6.28 mm, 6.28 coils. So which can be rounded up to 7 coils, because there won't be any fraction number of coils. We'll round it to 7 number of coils. So therefore n is known. Then the remaining things are same. Total number of coils is, again we'll assume ground and square and ground ends. So for a square and ground ends, number of inactive coils is 2. Therefore, your total number of coils will become 7 plus 2, which is 9. Nt is 9. So this is how we can compute the total number of coils. So then finally, the free length of the spring. What do you ask? So free length is nothing but, for free length, you should have what is the solid length, what is the maximum compression delta, and also what is the total gap or clash allowance. So in this particular problem, he has given that clash allowance is 15% of. If you read the last statement in our problem, he mentioned that clearly. He mentioned that the clash allowance. Okay. Here, so assume that the clearance between the adjacent coils or clash allowance is 15% of deflection under the maximum load. So now you have to use this condition. Don't assume the gap between the two coils and then multiply number of coils minus 1, so that you will get the total gap. So you cannot use that one. What we did in case of the previous problem, you cannot use that, because here he has clearly stated that you need to assume the clash allowance as 15% of deflection under the maximum load. So therefore, in order to calculate this clash allowance, first you should know what is the deflection of the spring under maximum load. So for that, we know the formula for the delta. So we'll use the same delta again, delta formula, to compute the maximum deflection. So here, delta formula is again same formula what we used earlier. That is 8 PD cube n by GD power 4. Here you need to consider P max, which is 300. D is 42 and n is 7. Just now we computed. So G is given as 81370 and small d is 4 mm. So if you substitute all those things, you got that one as 11.15 mm. So once you got the delta, then you can calculate this total axial gap, or here is given. So solid length of the spring is straightforward. Total number of coils multiplied by the wire diameter. Total number of coils is 9 and wire diameter is 4. It comes out as 36 mm. And total axial gap is given as, this is what he has already given in the problem. So that's why we are taking it as 15% of delta, which comes out as 15.15 into 11.15, which comes out as 1.67. So therefore, the formula for free length of the spring is given as solid length 36. Total axial gap is 1.67 and delta is 11.15. So if you sum up all those three, you got it as 48.82 mm. 48.82 mm as the free length, so which may be rounded up to 50 mm. So once you have a free length, then finally you can find out the pitch of the spring also. Pitch of the coil, which is nothing but free length divided by total number of coils minus 1. Free length is 50 mm and total number of coils is 9. 9 minus 1 is 8. If you substitute that, you get pitch as 6.25 mm. So like this, you can design the spring for the given parameters. But here the only thing is, so this problem and previous problem both are same only. What is the difference in this problem is, he has given the delta value indirectly, or he has given the two loads and he has given the change length for those two loads. So from that we use that relation, we can compute the stiffness of the spring also. So using that relation only we calculated these things. Not only that, so in the beginning he put some constraint on DI. DI should be 20 mm only. So now how we incorporated that one in the design of the spring? First we incorporated the DI, that means by writing D in terms of DI, we incorporated that. But since we don't know what is D and capital D and small d, or we don't know C, we assume initially K is equal to 1 and we determine the diameter of the wire, and after determining the diameter of the wire, we recalculated the diameter of the mean coil diameter, and then we computed the C value, and then we compute the K value. So that is wall stress correction factor. Now using this wall stress correction factor, we recalculated what is the induced resultant shear stress in the spring. And after calculating that induced resultant shear stress due to this maximum load of 300 newtons, we checked that for the allowable stress. We checked this value against the allowable value. Since this value is less than the allowable value, so then your design is safe. So these things you need to do it. Whenever it is twisted something like this, the problem is you have to do like this only. So first problem is straightforward. He has given the data. So simply you have to substitute the data in a step-by-step manner and you can easily solve the problem. Coming to this problem, he has given some constraints on the mean coil diameter, or that is in the form of a DI should be 20 mm. So therefore, not only that, he has given the delta L. Instead of delta, he has given the delta L. So that you need to remember or observe here in this particular problem. Okay, maybe sometimes they may change some other data also, but the only thing is, okay, always the problem comes here. Then if you have two unknowns, if you don't know capital D and small d, then you cannot compute K here. So therefore K and D both are unknowns. So if K and D both are unknowns, then two unknowns is one equation, you cannot solve it. So in such situation, you have to follow only this procedure. First you have to assume K is equal to 1, then determine the diameter of the wire. Once you've done that, again recalculate all the parameters and try to find out what is the resultant shear stress. Then you need to check for whether this induced resultant shear stress is less than the allowable shear stress or not. So this is the important thing. Once you have done that, then the remaining thing is going to be as usual procedure. So you have to observe this difference in this particular problem. Okay, right. So now I hope it is clear to you. Or anybody having any doubt, then you can ask your doubts also. So everything is clear, then we will move on to the next problem. Or if you have some doubt, then we will discuss your doubts. So anybody having any doubt? I think no response. I don't know whether you are following it or not also.
No, sir.
Somebody has typed something in the chat box. Yes, sir. 10:45. 10:45 అంటే ఎప్పుడో కదా. Okay, maybe note down చేశారంటే yes sir అని చెప్పుకుంటాడు. Okay, so now if it is clear, no doubt in this, then we'll move on to the next problem. So you note down this problem also, then we'll discuss the solution also. Okay, so I'll give 2 to 3 minutes for this one also, then we'll discuss the solution, right? Why it is going off? Right. All right. I don't know. Wait, I don't know why it is going off now and again. Yes, now note it down. You note down the problem, then we'll discuss the solution. So we'll say this is the problem on extension spring. Earlier two problems on compression spring, now this is on tension spring. Is it over? Put it down. Did you done it?
Yes, sir.
Okay, right. So, like already mentioned, this problem is on tension spring. So, you can see the figure also. The application is some kind of weighing machine. You can see weight is attached here. So, the weight is showing on the scale here. So, the spring is elongating here. It's not compressing. If you attach a load to the spring is elongating. So, therefore, it is a tension spring. So, now if I read the problem, a helical tension spring is used in a spring balance to measure the weights. One end of the spring is attached to the rigid support, while the other end, which is free, carries the weight to be measured. So that's what you can see it here. This end is hinged here. This end is free. Here you can attach the load. The maximum weight attached to the spring balance is 1500 newtons. So here you can see that the maximum weight attached to the spring is 1500 newtons, and length of the scale should be approximately 100 mm. So the total length is 100 mm. So that means here the spring can elongate a maximum of 100 only. So it cannot go beyond that. If the spring is elongated more than that also, the scale shows only 100. So that means you have a scale which can measure a maximum deflection of only 100 mm. So that means for this application, your delta max should be only 100 mm. The length of the scale should be approximately 100 mm. The spring index can be taken as 6. The spring is made of oil hardened and tempered steel wire with ultimate tensile strength of 1360 Newton per mm square and the modulus of rigidity of 81370 Newton per mm square. The permissible shear stress in the spring wire should be taken as 50% of the ultimate tensile strength. Design the spring and calculate wire diameter, mean coil diameter, number of active coils, required spring rate and actual spring rate. So two other parameters what he asked here is, he asked us find out what are the what is the required spring rate, but what is the actual spring rate here. So other than that, the problem, everything is similar to the first problem here. He has given the maximum load is 1500 newtons, delta max is 100 newtons, 100 mm, and he has given the allowable shear stress, and even he has given the spring index also. Everything is given. Simply you need to substitute the data into the problem. Okay, so now if I go to that, this is the given data. P is 1500 newtons, C is 6, SUT given it as 1360. Is it correct? Yes, it is 1360 only. Then G is given 81370, tau is 0.5 SUT. So all these parameters is given. First we will try to compute what is the diameter of the wire. Before that, using this relation, we will compute what is the allowable shear stress. So which comes out as 680 Newton per mm square. 0.5 SUT is nothing but 680 Newton per mm square. Then he has given the C value as 6. For 6 C is equal to 6, your K is 1.2525. Then we can compute what is the resultant shear stress, which is using this relation K is equal to 8 PC by pi d square. So here I use C instead of D, I use the C because he has given the C value instead of D value. No need to compute the D value also. Okay, anyway, later we'll compute that. So for that, 8 PC by pi d square, which is 680. 680 is equal to 1.2525 into 8 into 1500 into 6 by pi d square. So using this, we'll compute the D value. D comes out as 6.5 mm, rounded up to 7 mm. Then your mean coil diameter is nothing but C into 7, which is 42 mm. So then you need to compute what are the number of active coils. For that, delta is given as 100 mm. You know everything, all this parameter except this n. If I substitute the corresponding data and if I compute it, I got number of active coils as 21.97. So which is going to be 22 coils. Then so this is what we asked us. So now we are not. I haven't shown that other parameters of the spring. This is for the design purpose. So I just shown the calculations for what is asked in the problem. So he asked us calculate only wire diameter, mean coil diameter, then number of active coils. After that, what is the required spring rate and actual spring rate. Required spring rate is nothing but K is equal to P by delta. We are applying a load of 1500 newtons and delta is 100. So required is 15 Newton per mm. But what is the actual spring rate? So actual spring rate is calculated based on the parameters of the spring. So this is the formula for stiffness of the spring. which is GD power 4 by 8 dQm. So if you substitute all those parameters, it comes out as 14.98 mm. So that means, so there is a little bit of error. If the stiffness is 15 mm, then if you apply a load of 1500 newtons, then it will, on the scale it will show 100 mm. So now if the stiffness is changing from 15 to 14.98, there is a slight error in the deflection of the spring, because you are applying the same load 1500, but the deflection is going to be 1500 divided by this 14.98. So then it is slightly more than 100 mm. Slightly more than 100 mm. That means, so there is a little bit of error in that one. So anyway, we are not bothered about that one. So in this particular problem, he asked us compute what is the required spring rate and actual spring rate. These are the relations you need to use. So required spring rate is from the requirement. So your load requirement and the delta reflection requirement. So from that you will get that. Actual spring rate is from the spring parameters. You will get the actual spring rate. So this is how you can solve this problem also. Okay. So now we'll stop the class at this point. Maybe in the next class we'll consider one more problem and we'll try to discuss another problem on the springs also. Maybe that is in a different manner. So the data is different in that particular problem also. So we'll discuss some more problems in the coming classes. Okay. Right. So I think if you have any doubt in today's class, now you can ask it. Otherwise, everything is clear. Then so just respond to the attendance sheet and then you can leave the class.